Hello friends, welcome. Today, we are going to tackle a topic that sounds a little scary to many people. That topic is linear algebra. But what if I told you that linear algebra is actually the secret language of artificial intelligence? It is the backbone of machine learning and data science. Without it, there would be no ChatGPT, Netflix recommendations, self-driving cars. It's that important. So, stick with me for the next few minutes. I promise to make it super simple and fun. We are going to break it down together, step by step, just like we always do. You might be thinking, Abhishek, why do I need math? I just want to code and build cool AI models. Imagine cooking biryani without knowing your spices. With the right spice knowledge, you become a master chef. Linear algebra is like those spices for AI. It gives you the fundamental knowledge to understand why your code works, helps you debug problems, optimize your models, and create new things that no one has thought of before. This is not a boring university lecture. We'll use everyday examples you can relate to, and some simple Python with NumPy. Think of this as your hello world for AI mathematics. We are starting from the very basics. No prior knowledge is needed. If you can count and have a little curiosity, you're ready. By the end, you'll have a solid, practical understanding of how linear algebra fuels the AI revolution. So grab a cup of chai, get comfortable, and let's demystify linear algebra together. Alright, let's start with the absolute basics. A scalar is just a single number. Temperature, 25 degrees. Your age, the price of a samosa. A scalar is a plain value with no direction. Now, a vector is a list of numbers. Grocery list. 2 apples, 5 bananas, 1 loaf of bread. The position gives meaning. Apples, bananas, bread. In ML, a vector can represent a data point. A house has 3 bedrooms, 2 bathrooms, 1500 SQFT. Stack vectors, and you get a matrix, a grid of numbers with rows and columns. Think spreadsheet or user movie ratings. A black and white image is a matrix of pixel brightness. 0 could be black, 255 white, and everything between is gray. Beyond matrices, we get tensors, higher dimensional arrays. A color image is a 3D tensor, 3 matrices stacked for red, green, and blue. Deep learning models work with high-dimensional tensors to represent complex data. Scalars, vectors, matrices, tensors. These are our building blocks. One of the most fundamental operations is the dot product. Your item's vector times the price's vector equals your total bill. You multiply corresponding elements, then add apples x price, bananas x price, milk x price. That sum is the dot product, a single scalar. In ML, we use dot products everywhere, measuring similarity. Same direction, large positive, opposite, large negative, perpendicular, 0. NumPy is a fantastic library for numerical computing. First, you import it. Import numpy as numpy, then create your vectors and compute. Items, dots needed, jajuk snapplot array, 10, 5, 2. Prices, snapplot array, 20, 5, 50. Total, bill, jajuk snapplot dot, items, needed, prices. Or use items, needed, offer, prices. Print, fee, the total bill is, total bill is. Output, the total bill is, 325. NumPy does the heavy lifting in optimized C Fortran. It powers SciPy, Pandas, scikit-learn, TensorFlow, pretty much the whole ecosystem. The dot product combines 2 vectors into one meaningful value. Total cost, document similarity, or a neuron's activation strength. Matrix multiplication is a series of dot products. Take a row of A with a column of B to fill one cell of the result. Example, a diet plan matrix. How many apples, bananas, carrots each day? times a nutrients matrix, carbs, protein per food, gives totals per day. Important rule: columns of the first equal rows of the second. Result shape is rows of the first by columns of the second. This matters everywhere in ML and neural networks where shapes must align. Define diet plan. Snapshot array 2, 1, 0, 1, 1, 3. Nutrients shape snapshot array 24, 0.5, 27, 1.0, 10, 0.9. Daily totals. Diet plan Ava nutrients. Print daily nutritional totals. Carbs, protein. Print daily totals. Output 75, 2, 81, 4.2. Matrix multiplication is the engine of deep learning, transforming inputs layer by layer. Let's talk about two essential operations: the transpose and the inverse. Transpose flips rows and columns over the main diagonal. A 3x2 matrix becomes 2x3 when transposed. It's a convenient way to reorganize data or make dimensions compatible for multiplication. In NumPy, AT, the inverse is like division for matrices. AX, A1, Chi, I, the identity matrix. Not all matrices are invertible. They must be square and have non-zero determinant. In ML, inverses appear in closed-form linear regression, normal equations. NumPy gives np.linealg.inverts. Example: import numpy as np. A san up.array san 2, 3, 4, 5, 6. A transpose san at. Print original matrix 2 is 3 or n. A print transpose matrix 3x2 or n. A transpose. B arth.array 4, 7, 2, 6. B inverse sum nup.linealg.inv. B print unoriginal matrix brn. B print inverse of matrix brn. B inverse. Identity B arrow B inverse. Print B multiplied by its inverse nup.round identity. Transpose helps reorient data. Inverse helps solve systems and appears in certain ML solutions. Now for the really cool part. Big datasets can have hundreds of features: area, rooms, age, distance to school, crime rate, and many are redundant. PCA reduces dimensionality by creating principal components, new features that are linear combinations of originals. PC1 captures maximum variance. PC2 captures the next, orthogonal to PC1. Under the hood, PCA builds a covariance matrix, then finds eigenvectors and eigenvalues. Eigenvectors give directions, components. Eigenvalues show how much variance each captures. Pick top components to reduce, say 100 features to 2 or 3, speeding training and enabling 2D 3D visualization that reveals clusters and patterns. PCA is a classic example of linear algebra giving an elegant practical solution in data science. How does a model understand words like king and queen? Word embeddings convert words into vectors, 50, 100, even 300 dimensions. Similar words end up close in vector space. King and queen are close. Car sits far away. Famous relation king, man, plus woman queen. Models like Word2Vec and Glove trained on massive corpora learn these vectors. Similarity uses cosine similarity, derived from the dot product, measuring the angle between vectors. Embeddings form the first layer of many NLP models. Translation, sentiment analysis, even chatbots like ChatGPT. Linear algebra powers it all. If linear algebra is the language of AI, neural networks are the brain. And matrix multiplication is how that brain thinks. Each layer takes an input vector x, multiplies by a weight matrix W to produce a new vector, then applies a non-linear activation. Outputs feed the next layer. Deep networks are chains of matrix multiplications interspersed with activations. During training, backpropagation, weight matrices update based on gradients, matrix calculus at work. All the knowledge a model learns, recognizing faces, translating languages, even driving, is stored as numbers in these giant weight matrices. When you hear about models with billions of parameters, that's billions of weight entries. GPUs are crucial because they perform massive matrix multiplications in parallel, very fast. Understanding matrices and multiplication is understanding the engine of modern AI. And there you have it, my friends. We toured scalars, vectors, matrices, tensors, the dot product and matrix multiplication, transpose and inverse, PCA, embeddings, and neural networks. It wasn't so scary, was it? Linear algebra shows up everywhere in AI, under the hood of the tools you use every day. Next steps: open a Jupyter notebook and play with NumPy. Create vectors and matrices. Multiply them with ERO or NP. Use AT and nemp.linealg.inv. Replicate today's examples. Explore scikit-learn's PCA. The more you practice, the more intuitive it becomes. Don't be afraid of the math. Embrace it. You don't need to be a math genius. A solid intuition will make you a better practitioner. If you found this helpful, hit subscribe, like, and share with a friend. Drop your questions in the comments, and I'll cover them in upcoming episodes. This was day 9 of our data science and ML journey. See you in the next one. Happy learning. Scalars, vectors, matrices, tensors, dot product, matrix multiplication, transpose and inverse, PCA, embeddings, neural networks, resources, NumPy, scikit-learn PCA. Thanks for watching. Let's make these abstract concepts come alive with visuals. Imagine a single dot on a number line. That's a scalar. It's just one value, like the temperature outside, or your age. Next, picture an arrow pointing from the origin to a point in space. That's a vector, a list of numbers, each representing a direction or a quantity. Think of a shopping list, where each item is a dimension. Now, let's stack several vectors side by side to form a grid. This grid is a matrix, with rows and columns, just like a spreadsheet, or the pixels in a black and white image. Each cell holds a value, and together they store complex data, from movie ratings to image pixels. But what if we stack multiple matrices together, like pages in a book? That's a tensor, a higher dimensional array. Tensors can represent color images, video frames, or even batches of data all at once. Scalar, vector, matrix, tensor. You'll see how these building blocks fit together to represent everything from simple numbers to the rich, multi-dimensional data that powers modern AI. Now that we've visualized scalars, vectors, matrices, tensors, let's see how they interact the dot product matrix multiplication. First, let's look at the dot product. Imagine two vectors, two arrows in space. The dot product combines them into a single number. It tells us how much one vector goes in the direction of the other. In data science, this operation is used to measure similarity, comparing two user profiles finding patterns in data. Next, matrix multiplication. Think of a matrix as a grid of numbers, like a spreadsheet. When we multiply two matrices, we're combining information from rows and columns in a special way. Each element in the result is the dot product row from the first matrix column from the second. This operation is the backbone of many machine learning algorithms. It helps us transform data, rotate images, and even train neural networks. Understanding these operations is key to unlocking the power of linear algebra in data science and machine learning. In the next scene, we'll see how these mathematical tools are used in real-world applications. Let's dive deeper. Two more essential matrix operations: the transpose, the inverse. First, the transpose. Imagine flipping a matrix over its diagonal rows, become columns. Columns become rows. This simple operation is crucial in data science. Align data for calculations like covariance switch perspectives in a dataset. Now, the inverse. Think of the inverse as the matrix equivalent of dividing by a number. If a matrix represents a transformation, its inverse reverses that transformation. In machine learning, calculating the inverse allows us to solve systems of equations, optimize models, undo data transformations. Both the transpose and the inverse are powerful tools, help us manipulate and understand complex data structures. Mastering these operations unlocks even more possibilities in data science and machine learning workflows. Now that we've explored the building blocks of linear algebra, let's unlock one of its most impactful applications in data science: principal component analysis, or PCA, and the art of dimensionality reduction. Imagine a dataset with dozens of features, or even hundreds of features. Visualizing or modeling high-dimensional data can be overwhelming, like searching for patterns in a tangled web. This is where dimensionality reduction steps in. PCA simplifies complex datasets by transforming them into fewer new variables called principal components. Those components capture the most important patterns and the key variations in the data. You can see the big picture without losing essential information. Here's how it works. PCA starts by centering the data, then finds new axes, directions where the data varies the most. Projecting the data onto these axes reduces dimensions, making visualization and analysis much easier. This relies on concepts we covered like matrix multiplication and transposes. Dimensionality reduction isn't just simplification. It helps prevent overfitting. It speeds up computations. It can reveal hidden structures in the data. In summary, mastering PCA and dimensionality reduction turns overwhelming datasets into clear, actionable insights, an essential skill in data science and in a machine learning journey. Now that we've seen how PCA can simplify complex datasets, let's explore how modern machine learning takes this concept even further, with embeddings and neural networks. Imagine you have data that isn't just numbers, words, images, or even sounds. How do machines make sense of this? The answer lies in embeddings, a way to translate complex, high-dimensional data into meaningful, compact representations. Embeddings are like creating a map, where similar items are placed closer together. In natural language processing, for example, words with similar meanings, like king and queen, end up near each other in a multi-dimensional space. Neural networks learn these embeddings automatically, uncovering patterns and relationships hidden deep within the data. But how do neural networks do this? At their core, they use layers of interconnected nodes or neurons to process data step by step. Each layer transforms the data, extracting higher-level features and learning intricate patterns. Embeddings are often formed in the early layers, setting the foundation for the network's understanding. These learned representations power everything from recommendation systems to image recognition and language translation. Embeddings and neural networks allow machines to interpret and operate on data in ways that were once impossible. In essence, while PCA gives us a glimpse into dimensionality reduction, embeddings and neural networks open the door to a world where machines can truly understand and reason about complex, real-world information. Congratulations! You've just navigated through some essential linear algebra concepts powering modern data science, powering machine learning, scalars, vectors, matrices, tensors. Visualizing interactions, dot products, matrix multiplication, you've laid a strong mathematical foundation. Transpose operations, inverse operations, PCA, dimensionality reduction, embeddings, neural networks. This is just the beginning. Linear algebra is a living toolkit. Build models, analyze data, solve real-world problems, keep practicing, experiment with small projects. Revisit these ideas as you progress. Ready to dive deeper? Next videos. Applications in real ML workflows. Start building your own intelligent systems. Stay curious. Keep learning. Thanks for watching. See you in the next chapter.